Yeah, so welcome everyone to this, I think, 22nd edition of the Global Medical Physics Education Lecture Series. It's my pleasure to have Honor Djam here for the second time. Actually, he gave a talk last September, so September of last year, on managing treatment interruptions in radiotherapy. And today he's going to be talking about sort of like historical treatment planning, namely using monitor unit calculations for calculating dose. So it is my pleasure to introduce him. He is a consulting physicist at One Physics, and
So how much time so there for the presentation? Hello.
yeah. So Honor, please share your slides and take it away.
Awesome. Awesome, everybody. Let me let me do this. The presentation will be for approximately about an hour. Um, what I recommend that we do is we should keep our questions until the end of the presentation. Um, so let's go ahead and start.
Let me know if you need help sharing. I think I have allowed it though.
Okay. I was like, what's going on? Let me redo this. Okay. All right. Okay. Can you see my screen now?
Yes, but not yet the slides. Honor just cut off. Give me a couple minutes while he gets his technical side working.
Oh, share screen. Okay.
Okay, there we go.
Sounds like I succeeded.
Okay, take it away, Honor.
All right, perfect. Hello, everybody. Thank you again for joining this short presentation on MU calculations. Today, one of the things that we will talk about, or the main topic that we'll talk about, really the whole objective of this talk really is to look at the concepts surrounding MU calculations. We'll look at some of the notations on how do we actually determine this dosimetric quantities, and then we'll look at the formalism. Now, it's divided into two parts. If time permits, we will do MU calculations for photons and electrons, but most likely the talk will be separated into two parts, where today I'm just going to focus in details MU calcs for photons, and then the second part, we're going to look at MU calcs for electrons. And the rationale is because it's not just looking at the MU calcs, we are looking at the fundamental physics surrounding the whole formalism. And so what we know is that in radiotherapy, every fraction of radiation counts towards a patient's survival and well-being. What this means is that precision in delivering that radiation isn't just a technical goal, it is the difference between effective treatment and unnecessary complications. And therefore, we technically do not set, we do not set patients dose directly at the console of a treatment unit. And the physician prescribes a dose, and the therapist enters a particular MU, a certain number of MUs to deliver the prescribed amount of dose. And so this begs the question to really define what an MU is. In other words, MUs are the units used to quantify how much radiation a linear accelerator needs to deliver to achieve a specific prescribed dose. In other words, in external beam radiation therapy, monitor units or beam on time is the parameter that we use to deliver the prescribed dose to the patient. And these MUs are typically calculated by the treatment planning system and by requirement must be verified within an accuracy of plus or minus 5%. Now, the number of monitor units required for a given treatment or the time setting if we're dealing with a cobalt-60 unit is often calculated and set for each individual beams. And by determining these MUs, it's really not as simple as setting a dial. It really requires a deep fundamental understanding of beam dynamics, patient anatomy, as well as machine calibrations and the various physical interactions involved. And so this presentation essentially is designed to guide us through the intricate process of MU calculations, essentially looking at its complexities as well as demonstrating this by some examples. And before I kick off my talk, I always want to look at some guidelines and standards that are available to help us as medical physicists, radiation oncologists do this. And for this particular presentation, I did use a couple. Predominantly, I use TG71 and TRS 430. Now, the Estro Book 3 and 6 and 9 have similar formalism. The only caveat here is that their variables are almost different, but TRS 430 and TG71 are similar in terms of how they define and the symbolism with which they use. And so as a disclaimer before this talk, I practice medical physics in the United States. And so I'm going to speak predominantly from TG71 and TRS 430. Now, there are other books out there that I could have recommended. If you need a list, we can always send that to you. And so computing absorbed doses in a patient using typically doses in patients are computed with the use of measured data in a phantom that that has been really has been the standard of practice in radiation therapy since I can remember. And the rationale of this is because direct measurement of absorbed doses in patients or in a patient is really impractical and often really impossible. Therefore, treatment planning systems often make use of calculation models since these measurements are not made directly in a patient. I thought that's something that we need to keep that in mind. And so the question begs ourselves is the accuracy of dose delivery is really crucial in radiation therapy. And here we are typically aiming for a dose accuracy of between 3 to 5%, which in turn translates into keeping our dose calculations as precise as possible. In other words, we should keep our dose calculations within 2%. Now, the level of precision matters here because even when you look at the TCP and NTCP curve, even a small variation of about 5% in dose can significantly impact treatment outcomes. For instance, it could change the probability of tumor control, by, between 10 and 20%, or the likelihood of complication between 20 and 30%, depending on where we are on the dose response curve for that particular tumor. Now, in radiotherapy, tumor control probability, in short TCP, generally is a parameter that we use to calculate the percentage of tumor killing, while its effect on normal tissue damage is often described by what we call the normal tissue complication probabilities. And so both TCP and NTCP depend on fractionation, cell biological effects such as repopulation, redistribution, repair, and reoxygenation. In this particular graph, D50 is the dose where half of the treated patient achieved the desired outcomes, essentially a benchmark, a benchmark dose. And the gamma that we use, gamma here, the slope itself is described by a quantity called gamma, which in turn describes the steepness of the dose response curve. Now, a steep curve means that a small dose changes leads to a large change in response, making accuracy even more critical. Now, what we need to keep in mind is that both random and systematic uncertainties are at play here. Now, random errors typically are more related to delivery variations, while systematic errors often come from calibration as well as machine setup issues. Now, systematic errors particularly are concerning because they don't average out over time. They accumulate, potentially affecting every fraction of the treatment. And so in advanced treatment modalities, which is a common practice today, such as, IMRT, uncertainties increase because of complexities of things like, organ motion, dynamic dose modulation, thus achieving the recommended 2% accuracy in those calculations is really essential for an effective complication-free treatment. Now, before we move on to the next slide, I want to, conclude here is that PET ICRU 24 recommends an accuracy in the delivery in the dose delivered to the target volume of plus or minus 5%. And this is estimated on the, let me put my pointer here. And this is estimated on the steepest region of the curve. However, in certain critical conditions, the needed accuracy could even be more stringent. Keep in mind that it could be the case for certain types of tumors where a variation of a maximum of about 3.5% of the dose could be delivered. That translates essentially to an accuracy that a required accuracy of about 2% that we need. And so when we look at the fact that, remember that those measurements are done in the water phantom, and therefore we use, calculation models in order to calculate the dose in a patient. And historically, the evolution of those calculation algorithms really over time tells us a story really of how technology really has advanced in medical physics, from adapting to improve accuracy and reliability in patient treatments. And so in this slide, I just want to go briefly to explain some of the evolutions in TPS, or in the calculation algorithms that we currently use. If you look at the curve, you realize that way back in the 1950s, they had just simple empirical models. Now, these were the first approaches to those calculations, and they were heavily based on broad beam data measured in water. In here, because of the unavailability of CT images at the time, patients' body contours were outlined in a simple 2D contour, and all calculations were done assuming for homogeneous water-like conditions. Now, common empirical approaches included calculating the percent depth dose, the tissue air ratios, and TPRs. And essentially, what this implies that these algorithms replicated input data, beam measurements in water, really without taking into account patient-specific anatomy, which limited their accuracy. If I want to give an example, you have the TAR method, or the TAR method typically combines, beam attenuation, as well as scatter effects to approximate the dose, which often ignores many complexities that we now understand, such as tissue heterogeneity in body parts such as the lungs. Now, in the late 1970s and onwards, we had the onset of correction-based algorithms were introduced. And this was predominantly because of the introduction of CT technologies in the 1970s, which then made more sophisticated algorithms very possible. One of the pioneers of this work is Cunningham's work that was published way back in 1972, which was essentially instrumental in combining empirical methods with corrections for tissue inhomogeneity. Now, when you look at correction-based algorithms, such as the ITER method that leverage CT data to correct, those calculations, typically based on varying tissue densities, they essentially separated the primary and the scattered components and used what we call the equivalent tissue ratios, and essentially relied upon the Clarkson integration methods to improve those calculations. Now, in our modern era, we have what we call the kernel-based algorithms. There are different ways of classifying these. Now, kernel-based algorithms here essentially represent a significant, when compared with correction-based algorithms, were far more advanced. And they introduced the concept of dose deposition kernels, which essentially describe how the energy is spread from a point of radiation interactions. Now, you can look at examples such as the pencil beam algorithms that simplify 3D problems into 2D convolutions, making it computationally less demanding. However, pencil beam algorithms are not very ideal for handling complex tissue inhomogeneities such as the lung. Now, you have the AAA algorithm, or the anisotropic analytical algorithm that is commonly used by Varian, and the collapse-Coon convolution methods essentially address these issues such as tissue inhomogeneity by modeling the lateral transport of electrons and correcting for 3D inhomogeneities. One of the things I want to mention here is that these algorithms each have their advantages and disadvantages, and we're not going to go into details here. I'm just giving you a preview of the various types of algorithms available out there that are used to model or calculate the dose in various TPS. Now, the gold standard are Monte Carlo algorithms, and what we need to keep in mind is that essentially MC methods simulates the interactions of individual particles through the patient's anatomy, and often using stochastic methods, which essentially means using random sampling to calculate the various particle interactions within the patient. And so the question then remains, why do we need manual MU calculations? Why do we need manual MU calculations? In general, manual MU calculations essentially play a very important role in ensuring the safety and accuracy of radiation therapy. Now, in accordance with ICRP report 86, which I recommend that you should take a look, it's an older report. it says in it that 28% of all incidents or accidents in external beam radiation therapy were due to errors in treatment planning and those calculations, as you can clearly see as shown on the graph. So a majority of the errors or accidents reported were as a result of treatment planning and those calculations. And the majority of these errors, as concluded in this report, stem from human factors, such as one, not fully understanding the treatment planning system, which means that as a medical physicist or radiation oncologist, dosimetrist, we really have to take time to have an intricate understanding of what is happening behind the scenes. Now, the second reason that contributed to this was inadequate commissioning. And the last was a lack of independent verification. Now, let's break it down. Now, when we look at the lack of TPS understanding, many errors occur simply because the users may not fully understand how the TPS works, leading to incorrect parameter settings or are unaware of the system limitations. Now, when we talk about inadequate commissioning, what I mean is that really, without a comprehensive, without comprehensive testing or proper commissioning, there could be inherent inaccuracies in the dose calculation models in our treatment planning system that go unnoticed. And therefore, there are so many resources out there that really gives us comprehensive step-by-step on different tests on how to check to make sure that these inconsistencies in our calculation models within our treatment planning systems are minimized. They may not be completely eliminated, but they can be minimized. And TRS 430 gives at least a set of 9 to almost 15 different tests just related to MU calculations, just to make sure that we can minimize or eliminate these inconsistencies. Now, one of the things that was emphasized in this report is the fact that in some centers, there were no independent MU calculation checks. And so the physicists, the oncologists at these centers relied solely on the TPS or MU calculations, which essentially means that any systematic errors were propagated undetected throughout the treatment planning process. And therefore, manual MU calculations essentially is a critical independent check which allows us to verify the output from the TPS and helps us to catch any potential discrepancies before they may impact, a patient's safety. Now, AAPM strongly recommends that an independent dose calculation be performed at all the key intervals in the treatment planning process. And typically, this independent calculation should be done at the ISO center or at the point near the center of the PTV or the planning target volume. What this does is that this verification step essentially helps us to ensure that the plan dose matches the delivered dose, in turn minimizing the risks of any systematic errors in the process. And so to summarize this, really, I cannot really overemphasize this. Manual MU calculations are more than just a double check. Essentially, they are a vital safeguard that adds an extra layer of assurance in our treatment planning process. In other words, by performing these checks, we essentially significantly reduce the risk of incidents occurring and ensuring a high level of care to our patients. We owe it to them to do this. And so TRS 43 essentially boils down these issues related to treatment planning errors that they can be summarized in 4 key words: education, verification, documentation, and communication. In other words, they strongly recommend that education is required at the time before commissioning or at the time of commissioning by all the stakeholders, medical physicists, oncologists, dosimetrists, therapists, to have an intricate understanding at the technical and professional level of what is happening behind the scenes in the treatment planning system. And really, this is a very important component in trying to understand what our software can and cannot do in various circumstances. Now, verification, remember that nearly 60% of all reported errors involve a lack of appropriate independent secondary check of our treatment plans or those calculations. And so verification, secondary verification is very important. Now, currently, most centers use another software, Radcar, ClearCheck, and so on and so forth to do a secondary verification. Also, as a medical physicist, my recommendation is when you look at the secondary checks, you need to have an intricate understanding of what is going on. Look at the point where the calculation is done. Is it an appropriate point? It should not be in a bone. It should not be in air. It should be located probably at the isocenter or towards the center of the PTV. All of these are simple things that you can do to make sure that the point and the calculation doses make sense to you. And they should fall within the limit as recommended by by the ICRP report. And so, according to ICRP report 86, a number of these incidents really may have been avoided with a systematic, in vivo dosimetry and independent TPS verification. Now, additionally, independent verification essentially can increase our trust in the precision of the algorithm and the reliability of the beam data that we collected during commissioning. In order to calculate the dose in a patient per AAPM TG71, it is essential that we really understand the process of dose deposition in a patient. Now, the process of dose deposition in a patient is very complex and requires us to consider both, attenuation and scattering of the radiation beam before and within the patient or within the phantom. And so let's start first by categorizing the different types of radiation involved here. And I'm going to break this down into 2. You have direct radiation, which essentially are the radiation or the photons or electrons generated at the source or at the treatment head, the linear accelerator, and reaches the patient or the phantom without any intermediate interactions. In other words, this radiation has a straightforward part, or in straightforward terms of its parts, this direct beam is responsible for a significant portion of the absorbed dose within a patient. Now you have what we call indirect radiation, often referred to as the heat scatter, which essentially involves photons that interact with components within the treatment unit, such as the flattening filter, the collimator, or other heat structures. Now, these interactions typically cause scattering, and the scattered radiation then reaches the patient. Now, this component is very crucial to account for because it contributes additional dose beyond the direct beam from the treatment head. Also keep in mind that we have what we call electron contamination. Now, electron contamination here involves electrons or positrons that are released from interactions either within the treatment head or from the air column between the treatment head and the patient. Now, this contamination can typically add to surface dose, which in turn can, depending upon the level and the magnitude, affect skin toxicity. Now, together, all these components, direct radiation, indirect radiation, or often called head scatter, and electron contamination contribute what we call the radiation output, which is essentially the radiation reaching the patient. Now, from the patient's perspective, this is what we call the incident radiation and typically and determines the actual dose delivered at the point of concern. And so, and so keep in mind that, therefore, to move forward, the dose, this kind of concept will repeat itself over and over as we go over this presentation. So the dose at any point in a patient or phantom, therefore, is a result of two contributions: primary radiation and scatter radiation. The scatter dose, keep in mind, becomes more significant as the volume of the irradiated tissue increases. This relationship essentially implies that field size and depth, therefore, are key factors in determining the extent of the scatter contribution. And so it is important to understand these components because they directly influence the accuracy of our dose calculation and the overall effectiveness of our treatment. This beautiful diagram that I love, it's still it really just really carefully illustrates the different components and the different of radiation that reaches the patient. You can clearly see that the radiation reaching the patient's surface originates from the primary source and from the components of the treatment head as a result of the primary particles interacting with these components. The thing I want to note here is at the various statistics here, head scatter photon radiation is also called extrafocal radiation if you read in other literature. So when you see the word extrafocal, it's just essentially head scatter. And essentially is the radiation that is scattered from the flattening filter, primary collimator, secondary jars, physical wedges, collimators, or MLCs. And the point I want to note here is that head scatter dose can amount to about 5 to 10% of the total dose reaching the isocenter. And even at large collimator setting, which means at large field sizes, can account for up to 12% of the dose that reaches the patient. Now, the scatter contribution increases as the volume of patient irradiation increases, which essentially implies that the scatter dose depends on the field size in the patient, as it is typically defined by what the collimation and the depth at the point of interest. And the statistics here is that the scatter contribution or the scatter dose typically accounts for up to about 30% of the total dose at the calculation point. And this is actually huge. Now, the primary dose dominates and represents generally more than 70% of the total dose within the patient. And so this figure here beautifully illustrates the various components involved from the treatment head and tells us a story of what are the various contributions that contribute to a particular dose in a patient at the point of interest. And so let's take a look back at trying to understand the factors that affect dose deposition in a patient. The dose deposited at a specific point within the patient is typically influenced by multiple physical parameters, all of which must be precisely controlled to achieve the desired therapeutic outcome, as well as to minimize the harmful effects to normal tissues or the surrounding organs at risk. The very first I want to talk about is beam energy. And beam energy here plays a significant role in how deeply radiation can penetrate into the tissues. You know, high energy beams are generally preferred for deep-seated tumors as they deposit, the maximum dose at a greater depth, reducing the dose to superficial tissues, speaking in terms of photons here. And this is based essentially on the characteristic depth dose distribution for photon beams, essentially where higher energies produce higher PDD values. The next factor here essentially is the beam on time, or which is measured in terms of monitor units and directly determines the total amount of radiation dose at the point of interest. Now, MUs are often calibrated to represent the amount of time the beam must be active to deliver the desired dose under specified conditions. When I use the word specified conditions here, I mean things like a particular reference field size, SSD, or the absence or the presence of beam modifiers, which essentially implies that calculating the correct number of MUs is really important in achieving accurate dose delivery. Also, a miscalculation here can either lead to an overdose or an underdose, both of which would have serious clinical implication. The next factor here is field size. Field size essentially affects the volume of tissue irradiated, which means that a larger field size will lead to more scattered radiation, contributing to an increased total dose beyond the primary beam. And so scatter radiation primarily is produced by interactions within the patient tissues. And well, there are two components of scattered radiation that we'll talk about later on. Then distance. Distance here could either mean SSD, source to surface distance, or source axis distance. And essentially is a key geometrical parameter that we need to consider here. The key physical parameter that dictates how distance affects our calculation, it goes through the inverse square law, which essentially describes how the radiation intensity diminishes with distance from the source. Now, as an increase in distance results in a significant reduction in dose, and this typically must be accounted for by adjusting the MU calculations, which explains why when you increase the SSD, what you're expecting is that the number of MUs to deliver the same amount of dose correspondingly increases. If you decrease the energy, the same happens. The next here are beam modifying devices such as wedges, trays, and spoilers, which in turn alters the dose distribution. Now, wedges often create, dose gradients across the treatment fields, which really are particularly very useful for compensating for uneven tissue contours and for sparing certain structures. Now, trays, on the other hand, are used to hold shielding blocks that shape the beam, in turn affecting dose distribution by introducing essentially additional attenuation. For those of you who do TBI, you may have encountered spoilers, which essentially are used to modify the surface dose, particularly in cases where increased superficial dose is required. And so when we look at the factors required in determining the MUs at a particular point, then you have beam energy, prescribed dose, field size, distance, as well as beam modifiers. And so talking about the concept of distance and depth here, distance play a crucial role through the inverse square law. Depth in this particular case refers to how deep the point of interest is within the patient or phantom. Now, the depth of the point in an attenuating medium such as tissue or water affects how much radiation is being attenuated. keep in mind that attenuation is influenced by beam quality or the energy of the beam, as well as the density and the atomic composition of the tissue. Higher beams tend to penetrate deeper with less attenuation, making it suitable for treating deep-seated tumors. Then you have here the next scatter radiation, which we've talked about, comes from two primary sources, the treatment head unit as well as the patient. Here, and so if we want to compare, I like this diagram. If you want to compare, let's say, look at the differences between 2 points, point P and point Q. The very first thing we notice is that point P is further away from the source than point Q. What that means is that per the inverse square law, the radiation intensity decreases proportionately to the square of the distance from the source, which means that since point P is further away from the source, it receives less radiation intensity. Now, point P itself is deeper, which implies that the attenuation at point P is significantly different from the attenuation at point Q. And the field size at point P is, larger than the field size at point Q, which implies that the scatter radiation at P essentially is greater than the scatter radiation at point Q. Now, if you look at this, there are three components here that essentially determines the dose at point P relative to point Q. You have the scatter component, the inverse square law, the distance component, as well as attenuation. All of these three factors must be taken into account to be able to compare the dose at point P with respect to the dose at point Q. And so the differences between these 2 points essentially arises from the depth differences, which in turn is due to the attenuation effects, the distance differences, which essentially is explained by the inverse square law effect, as well as the field size differences because of the different scatter contributions at different field sizes. And so the next section of our presentation will begin to look at the formalism of MU calculations, taking into consideration all the factors that we have actually talked about. I see a note here. If you have a question, you can just wait until the end of the presentation. And yes, I'm going to send this slide to Joe, and he will distribute it to everyone if you're interested in having the slides. Now, one of the things that is very important that has often led to errors in MU calculation is the confusion between normalization conditions and reference conditions. And TG71 spends a great deal in that report trying to explain the difference. And so this slide here really I've tried to really capture the differences such that it makes sense. Now, normalization conditions are fundamental to how we conduct those calculations. Typically, the normalization depth, D0, as referred in TG71, is typically set at Dmax, the depth of maximum dose, and serves as a point where we can simplify dosimetry. Now, this helps in standardizing calculations by making relative parameters equal to 1 at that particular point. So I want you to think of normalization depth as an agreed upon benchmark within the patient's body or phantom to streamline our calculation and to reduce complexities. Let me give an example. For example, in a 6 MV beam, where Dmax is around 1.5 cm. Now, this depth is where the beam energy reaches its watt peak. So it's convenient to use Dmax as a standard point for comparison. Now at Dmax, all relative measurements, such as the total scalar factor SCP, tissue phantom ratio, for example, are all set to unity at that particular point, which in turn makes our MU calculations straightforward. Remember that these conditions are more about practical usability in our day-to-day calculations rather than absolute measurement accuracy. Now, calibration or reference conditions typically are about determining precisely how much dose we are delivering, where normalization allows us to apply relative dosimetry to different parts of the patient pretty consistently. And so TG51 describes our reference conditions or calibration conditions very precisely, while TG71 talks about normalization conditions very precisely. And you should keep that in mind. So calibration is conducted under reference conditions and as defined by TG51. And these conditions typically ensures that we are delivering an accurate absolute dose to the patient. So you have to think about calibration as a fundamental benchmark, a process where you make sure, for example, let me use this example, that your car speedometer, in which in our case, the linear output matches the actual speed. So you know you are delivering the right dose. And so during calibration, we essentially use an ionization chamber placed under reference condition defined by TG51, which typically are a depth of 10 cm in photons in water with a field size of 10 by 10, right? Now the reference depth for photon beams is set to 10 cm in water. Keep that in mind. The normalization depth is typically set to Dmax. Now, in all the clinics that I've practiced in that I've seen, the normalization depth is set at Dmax, even though TG71 recommends that we should keep the normalization depth at 10 cm because the reference condition per TG51 is set to 10 cm to kind of keep the consistencies. Because if we set, for example, the complication arises that we calibrate our machine and the reference depth is 10 cm. For photons, the reference depth for electrons is defined by R50. Now, keep in mind that, which is in turn different from the normalization depth, which means that we need to convert the dose at the reference depth to the dose at the normalization depth. We can do this through several methods, which I'm going to show you. So TG71, to avoid this conversion that could introduce errors and uncertainties, they want us to keep our normalization depth at 10 cm. I have not yet seen a clinic that is doing that so far for all the clinics that I've worked at or consulted with. And so it is important to note that normalization conditions are set primarily for convenience and consistencies in the calculation process, while reference conditions are established for calibrating the machine to meet, stringent accuracy requirements. And so it's important to kind of distinguish the difference. Here's an example of both conditions on this slide. On the one hand, you have normalization conditions where the normalization depth D0 is set to Dmax. On the other hand, you have the reference depth per TG51 is set to 10 cm. And so when you do your TG1 calculations for your monthly QAs, you can clearly see here per TG51, GQW is equal to the corrected metal reading KQ multiplied by NDW cobalt 60. I don't want to go into details of this equation. That's another topic of its own. But the attention I want to draw to you here is that when you look at the dose to water at 10 cm depth, it's calculated to be 0.666, which is less than, but then the dose to water at Dmax it's then converted to dose to water at Dmax such that at Dmax it's equal to 1 centigrade or approximately 0.998. And so here the calibration is done at 10 cm, and then you can see that it's converted to the dose at the normalization conditions to keep it consistent in this particular case. I was just looking at the data from the Radiological Physics Center in San Antonio. It indicates that 90% of clinics that they monitor typically perform their dose normalization at Dmax rather than at 10 cm, which is allowed within the protocol as long as the normalization depth is at or beyond Dmax to account for electron contamination. And so let me give an example here. Suppose a clinic has been using a non-isocentric setup with an SSD of 100 cm. Under these conditions, 1 mu essentially correspond to 1 centigrade at Dmax. And now they transition to an isocentric setup where the SSD is 100 cm and the normalization depth is 10 cm. How do we convert between these two conditions? Now, per TG721, in order to do so, you essentially multiply the dose calculated at the reference depth with the TMR corrected for the inverse square law here. And they actually gave us a beautiful table to show us how this has been done. You could look at, this is the energies, the various depths, the TMRs, correction for inverse square law, and you can see here that essentially this is multiplied with this, and the dose is converted from here to here by simple multiplication. So this really demonstrates one simple way where you can essentially convert from the reference point to the norm point as well. Now there are two ways Yes, we're going to share the PowerPoint slides. So you don't need to worry about that. There are two ways. There are two formalisms with respect to photons that we can use to calculate the MUs. You have the isocentric method using the TPR, as well as you have the SSD method. Now, just to briefly go through this, so MU is equal to the prescribed dose divided by this here is the dose per monitor unit under normalization conditions. Understand that you have to convert the dose from reference conditions to normalization conditions. You could either use the TMR for isocentric method, or you can use the PDD for the SSD method. I'm going to demonstrate with some examples, so don't worry about it. This X here represents the off-axis distance, which essentially is the distance from the central axis of the treatment beam to a specific point of calculation. And understand that this distance is measured in a plane that is perpendicular to the central axis, specifically at the isocenter of the beam. Now, RD, just so you understand the various factors here, RD represents the equivalent square field at a particular depth within the patient. The equivalent square field at a particular depth within the patient. I'm going to explain what this means. D is simply the depth, and OAR Here is just the off-axis ratio. The off-axis ratio. SC and SCP or SC, which is essentially SCP, which is the product of SC and SP, essentially represents the in-water output ratio, which essentially is the ratio of the dose per MU in a phantom for a given field size to the dose per MU for the reference field size, which typically is a 10 by 10. Understand that SCP is measured at the normalization depth within the water phantom, and essentially it depends on both the colorimeter field size and the normalization depth. The increase in dose due to field size can come from both increase in energy flowing originating in the colorimeter head and scatter from within the patient. You have SP, which is the phantom scatter factor, and SC, which is the colorimeter scatter factor. We're going to talk about these terms in greater detail. Now, note that if we are to calculate the MUs, this formula here is the general formula of us calculating the MUs at an off-axis point X. If we're calculating the MU at the isocenter, the OAR here becomes 1, and this equation simplifies to this. And so in the case where the dose is calculated at the isocenter point, you realize that the OAR becomes 1, and the equation simplifies to this. This is to correct for the inverse square law in the equation. Here you have here the Tre factor. Now the PDD, or the non-isocentric method, which essentially is a little bit more complicated compared to the isocentric method, is calculated using the PDD. And everything really stays the same except for there's now a difference in the inverse square law here. Now, when you see here, I've put an X here. This is the equivalent square field. In this particular case, the equivalent square field at the normalization depth is given by the equivalent square field on the surface in bracket SSD plus D naught divided by SAD. Not this formula here is still tied to the formal slide, so keep that in mind. We're going to do an example, and you'll see how this is calculated. Let's look at some of these quantities in detail, which I think is absolutely very important in order to understand what these parameters in this equation actually mean. TG71 discussed this in detail, and TRS 430 for in TG71, it's under a topic called field size determination. Keep in mind that many dosimetric functions, such as percent depth dose, tissue air ratios, tissue phantom ratios, are field size dependent. And this dependency arises from the variation in the scattered radiation that originates either from the colorimeter head or the phantom. The key aspect here is really the scattered radiation contribution. As the field size increases, more of the radiation is scattered by the colorimeter and within the patient or the phantom, which in turn adds up to the primary beam contributing to dose within the patient. Now, in practice, keep in mind that in practice, it is impossible to measure every field. In other words, in practice, not every field is a perfect square. And when we really think about it, tumor geometry, patient's anatomy, the shielding requirement required often produces irregular fields. Now, to handle this situation, the concept of equivalent square fields are used. Keep in mind that the equivalent square field concept is essential in clinical dose calculation because it is impossible to measure every potential field shape and size individually. And so what do? We use interpolations to estimate the quantities that depend on both the scatter and the primary radiation. And so the equivalent square field is defined as the side length of a square field that produces the same scatter air ratio or any related dosimetric quantity as the field being analyzed. In other words, essentially, it simplifies the analysis of a known square field, such as rectangles, circular or irregular fields, into an equivalent square field that is comparable, that has comparable dosimetric properties. And to calculate the equivalent square field, there are several methods, but for the sake of time in this presentation, I'm going to present just one, the Stirling's formula, or what we call the 4A divided by P method. Now, the Stirling formula essentially asserts that equivalent square, or for a rectangle and a square to be equivalent, they have to have the same area of a perimeter. And so if you look at the rectangle here, the area of a perimeter is essentially WL divided by 2W plus L. And for this rectangle to be equivalent to this square, the A over P must be equal. And so if you equate this expression and this expression, remember that A over P here is equal to S over 4. When you equate the two expressions, then the equivalent square essentially will be equal to this 4 goes over, will be equal to 4 multiplied by the area divided by the perimeter. Now for circular fields, we can derive the formula very easily. For the sake of time, we will not do that here. And it's equal to 4 divided by the square root of pi multiplied by A over P. Now, one of the things that I want to mention here, which is very important, is that this formula, keep in mind, this formula provides a reasonable approximation for most fields. But the question I want to ask is, where does it lose its accuracy? When we are dealing with a highly elongated fields, for example, a 5 by 40, or let's say a 3 by 30, this formula becomes inaccurate. And the calculation is recommended to be, verified against direct measurements. So keep that in mind. The calculations must be verified against direct measurements. And so just a few things to note here. One, in some cases, there are some fields that are highly irregular. In this particular cases, irregular fields can be approximated as a triangle, essentially by determining its total area and adjusting the dimensions to create an equivalent triangle that maintains the same or approximately the same total area. Now, this method essentially implies that once this triangle is determined, the equivalent square field can be calculated either from the Stirling formula or using tabulated values. And some of these tables are actually given in kind. I should take note of. Now, some challenges or consideration when using the equivalent square field. One, like I said before, highly elongated field. And for highly elongated fields, keep in mind that the Stirling formula typically may not provide sufficient accuracy because it doesn't properly account for the varying contribution of scatter from the long side versus the short side. And in such cases, my advice is to verify the calculated equivalent square field using a more accurate method or simply direct measurements, especially when we are dealing with critical dose regions. The next point I want to make consideration I want to give here is one, the field size impact on output ratios. Keep in mind that in-air output ratios, or simply SCP, which essentially represents the ratio of the energy flowing in air for a given fuel to that of the reference fuel, are influenced by fuel size. And so the use of equivalent squares for calculating such ratios typically should be done with caution when dealing with non-standard fuel shapes. And this is essentially to ensure that the fuel characteristics match those used during calibration. And we are also going to talk a little bit after this about the colorimeter exchange effect that in turn affects some of these calculations. Now, this table I actually took off from Karen that gives us tabulated values of equivalent square fields that we can actually use. I recommend that you should take a look at this table. The next thing I want to talk about here that's very important is the total scatter factor or fuel output factor. If you've noticed, the word output is used very loosely in medical physics. And so in every conversation, I recommend that you should try to understand the context because it means different things in different contexts. Now, keep in mind that the fuel output factor is defined as the ratio of the absorbed dose per MU at the reference depth in a full scatter phantom for a specific colorimeter setting to that of a reference field geometry, typically 10 by 10. And essentially, the total scatter factor SP quantifies how changing the fuel size affects the dose at a particular depth. And how do we measure this? When you look at the graph here, the solid line indicates how the total scatter factor changes with changes in fuel size. And you can clearly see that as the fuel size increases, the output factor also increases. And these are all normalized to 1 at the reference fuel size 10 by 10. And the reason for the increase in the fuel output factor is simply because as the fuel size increases, we know that both the amount of scatter generated in the treatment head and the scatter generated within the patient also increases, which explain this exponential increase. Now, notably, if you look at the phantom scatter factor and the colorimeter scatter factor, one increases a little bit faster than the other, and we're going to explore the reason why this is the case. Now, before we move forward, for rectangular fields, special care essentially must be taken to distinguish between the upper jaw and the lower jaw because of the colorimeter exchange effect. And what do I mean by that? The upper jaw, the distance from the source between the upper and the lower jaw is essentially different, which means that they have slightly different fuel sizes. And this introduces inaccuracies in the calculation of the total scatter factor. And so we have to take special care not to introduce the inaccuracies. And there's a school of thought that says that this can be neglected because it's typically less than 2%, but still it contributes to the overall inaccuracies in our calculations, and I feel that it warrants our attention here. When we think about, and so the question is, when we're measuring the total scatter factor, SP or the phantom scatter or the colorimeter scatter, which fuel size do we use? Because depending on the treatment machines, the fuel size can either be defined by jars or by MRCs or blocks. And so in order to answer this question, we need to essentially look at the different treatment machines available out there. And I'm going to speak predominantly for the main ones. And before I do that, keep in mind that the difference in distances from the target from the target to the upper jaw and lower jaw results in deviation from the equivalent square model. And we call this the collimator exchange effect, which in turn describe the differences in output when the upper jaw or the lower jaw settings are reversed. Now, the upper jaw and the lower jaw are collimators that are closest to the target, to the radiation source, and are typically used to define the initial field size and to shape the radiation beam. Now, for open fields or externally blocked fields, the collimator scatter factor is typically determined by using the field size defined by the upper and lower jaw at the isocenter. But keep in mind that the upper jaw and the lower jaw are at slightly different distances from the source. Sometimes, to make our calculations simpler, we simply approximate that both are at the same distances to simplify our calculations, which in turn introduce some minute inaccuracies in our calculations. But interestingly enough, when we look at how variant machines versus Electa machines, you can see that the position of the MLCs in relation to the jaw really differs depending on the manufacturer, which in turn affects how we can define the field size. Now, for Electa machines, the MLCs are designed essentially as a replacement of the upper jaw. Keep that in mind. As the MLCs replaces the upper jaw, which implies that for Electa systems, when MLCs are used, when MLCs leaves are used to shape the beam, the equivalent square should be determined based on the MLC block field area. So which means that when you are doing your MU calculations, depending on whether you are dealing with Electa machines or with variant machines, you need to now, it will kind of affect what defines the field. Now, for Siemens machines, which I haven't seen one in the past couple of years, I've worked on one before. Now, the MLCs are typically designed as a replacement of the lower jaw, and also similar to Electa, the equivalent square should be determined by using the MLC block field area to determine the collimator scatter factor for Siemens systems. Now, variant is really different because they use what we call the tertiary collimation system, right? Now, variant machines often or uses the MLC as a stationary collimator placed below the standard jaws. What this means is that the equivalent square of the collimator field size is what is used to determine the collimator scatter factor. Now, for some calculations, just as an added note here before we move on, for some calculations, especially involving SP or the phantom scatter factor, it is essential to consider the field size at the point of calculation or the surface of the patient, depending on the situation. Because, the phantom scatter factor essentially accounts for the radiation scattered within the phantom or the patient and essentially depends on the irradiated field, the irradiated volume within the patient. And so the field size argument for SP is defined by the area that is incident on the patient, which in turn changes depending on the following conditions. One, if the radiation field is shaped by blocks or MLCs, the field size at depth is used for SP calculations. Now, the field size can be smaller or larger depending on factors like the tertiary blocking, as well as extended SSDs or other modifications that you need to take into consideration here. Now, when you really want to look at this, the important point I want to pass across here is the fact that, one, the collimator scatter factor, also known as the in-air output factor, essentially accounts for the change in the scatter radiation originating from the head of the treatment unit as the field size is changed, and we simply define it as the ratio of the output in air for given field size to the output in air at the same point for the reference field size as well. And keep in mind that for open or externally blocked fields, the field size is defined by jaws at the ISO center of the machine. And so when you look at this slide, it essentially shows how the scatter factors, the collimator scatter factors and the total scatter factors is changes as the field size increases. The question I want to ask is why the difference before the reference field size and after the reference field size, why does SCP increase rapidly compared to SC? Think about that. And keep in mind that the beam output increases with an increase in field size due to the contribution from collimator scatter, right? So as field size increases, the scatter component from the collimator jars also increases, which in turn adds to the primary dose, which in turn implies that SC increases as the field size gets larger. Now, to measure the collimator scatter factor, we typically use an ion chamber with a build-up cap. Keep in mind that SC can be measured directly with an ion chamber with a build-up cap because we're doing these measurements in air with respect to the Bragg cavity theory. We require a build-up cap to ensure electronic equilibrium because we the Bragg cavity theory only works as long as we have established electronic equilibrium. And so by using a build-up cap, we ensure that we can provide an electronic equilibrium. And so the setup, therefore, typically involves placing the chamber in air and measuring the radiation at various field sizes, which are then normalized to the reference field size. And in this particular case, or in the clinics that I work out of, the reference field size is always 10 by 10. Now, the ionization readings that we get are plotted against field size, as you can see on the graph, or calculated using the Stirling's method. Now, what you need to keep in mind is that a lateral margin of at least 1 cm from the field H is typically used to ensure that the penumbral effects do not interfere with our measurements, to ensure that the penumbral effects really do not interfere with our measurements. Now, we can also, if you look at the previous slide, where this diagram I took from Khan, where it shows us the measurement of SC in air. This here shows us the measurement of the total phantom scatter in medium or in a phantom. Another method that is also commonly used to measure SC is with the use of what we call the mini phantoms. And this typically is used for high energy beams. Now, the reason in-air measurements is really not recommended for high energy beams is because we need a very large build-up cap because of the increased distance that the scattered electrons will travel to be able to establish electronic equilibrium. And so for high energy beams, therefore using traditional build-up cap is impractical because they need to be very, very large, particularly for very small field sizes. Now, mini phantoms, which typically are cylindrical chambers with a diameter of about 4 cm, are often used instead of a build-up cap to measure SC. Now, the depth of measurement is often set beyond Dmax, typically at 10 cm, to avoid electron contamination and to help maintain consistent scatter contribution to the dose measurements. Now, this approach ensures that the scatter contribution from the phantom is consistent across measurements, which effectively cancels out its influence for larger field sizes. Some of the challenges that we might face when using the mini phantom is that for small field sizes, the mini phantom may not be completely covered by the beam. For small field sizes, the mini phantom may not be completely covered by the beam, which in turn may lead to inaccuracies because scatter from the phantom itself becomes very non-uniform. Now, what do we do in such cases? In this particular cases, metal build-up caps or e.g. brass are typically used for better shielding. Now, this approach essentially helps to minimize issues that are related to the electronic equilibrium and the spectrum changes, although normalization to 5 cm field size is recommended in this case for consistencies. Now, here I want to give you a few considerations before we move forward to think about here. Now, the position of MLCs with respect to the jaws affect the collimator scatter factors. Keep in mind that for Electa machines and CMN machines, the MLCs are designed to replace the upper and lower jaw, respectively, meaning that the shape defined by MLCs must be considered when calculating SCs. This is not the case for variant machines where the MLCs are below the jaws, which means that SCs can be determined using the main collimator opening only. And this is because of the impact of backscatter from the MLCs to the monitor chamber is minimized in variant machines as opposed to Electa machines where they are not minimized. Now, the next thing I want you to take note before we move forward is that when using shielding blocks, for example, MLCs or wedges, this not only reduce scatter from the collimator, but also introduces new scatter from the blocks themselves and any supporting trays. And this additional scatter must be accounted for in our SC values, especially when the field shapes involves heavy blocking or irregularities. And lastly, the value of the collimator scatter factor is generally assumed to be independent of the distance from the source. Now, keep in mind that it follows an inverse square law for output in air. This assumption, in my perspective, is not strictly true because the scatter radiation contribution from the head component may vary slightly with distance and field size. And there are several studies out there, several papers, for the sake of time that I actually do not want to put here, we should only prolong the length of this presentation, that have shown that variation in field size results from three important factors. One, the shielding of scattered dose from the flattening filter, which decreases as the field size increases. Now, the second is backscatter from the jaws to the monitor chamber, which also decreases with increasing field size. And lastly, small angle scatter from jaw surfaces, which increases with larger internal jaw surfaces. Now, before we move forward, keep in mind that the collimator exchange effects refers to the discrepancies that occurs when the setting of the upper jaws and the lower jaws are reversed. For example, a 5 by 40 field versus a 40 by 50 or 40 by 5 field. Now, this effect can lead to slight variation in the measured value in the collimator scatter factor. And typically, it's less than 2%. It's not insignificant, it's not significant. So it really depends on the physicist on site to determine whether to ignore this or not. And so it is recommended to determine the magnitude of the collimator exchange effects for large fields or for large clinically relevant fields, and to verify the accuracy of the calculations done by our algorithm. When we think about the phantom scatter factor, which essentially represents the variation in scatter radiation originating from within the patient or the phantom as the field size changes, what we need to keep in mind is that it essentially corrects for the scatter dose contribution from the irradiated volume to the dose measured at the reference depth. And so essentially, SP is independent of the radiation from the collimator and solely is related to the scatter produced within the irradiated volume itself, and solely depends on the volume within the irradiated volume itself. Now, keep in mind a few things that I want to mention. There are different ways by which the phantom scatter factor can be measured. It's actually easier. Well, there are different ways by which the phantom scatter factor can be measured. We can do direct measurements using varying field sizes, in which case SP can be directly be measured by changing the effective field sizes in a full scatter phantom. And in this particular case, we need to use additional shielding blocks while keeping other parameters constants. However, the limitations of this approach is that as the blocks can shield some of the scatter originating from the main jars, but also generate scatter from within its own, that can lead to inaccuracies in our measurements. Now, the most popular method that is used to measure SP is typically to use the mini phantom approach, in which case we in turn mitigate the issues arising from using blocks. What happens is that mini phantom is used, which is typically a very, very smaller phantom, which also helps to minimize the unwanted scatter radiation from the shielding blocks or collimator. Now, there is another method which is called the volume ratio scatter method, which I'm not gonna discuss here, that is also typically used. Now, from my perspective in clinical practice, is that what happens, keep in mind that the total scatter factor, which is SCP, is essentially the product of the collimator scatter factor and the phantom scatter factor. We can easily measure the total scatter factor. We could measure the collimator scatter factor. So we can use these two and simply divide the total scatter factor and the collimator scatter factor to get our phantom scatter factor. That provides a much more practical and an easier way for us to get our values. The next important thing I want to talk about here are normalized depth dose curves. Essentially, PDDs represent the absorbed dose at a given depth to the absorbed dose at the reference depth. And typically, Dmax is used, even though some cases, some people use surface doses, but in all the clinics that I've worked out of, we use Dmax as our reference depth. And it's typically expressed as a percentage ratio. Now, there are a couple of key things that I just want to mention in which TG71 emphasizes that we should think about when we are measuring PDDs. One, PDD value depend on the SSD used during measurement. This is because the distance factor or inverse square law affects the dose ratio at different depths, which implies that each PDD value is always tied to a specific SSD. So if you want to use a PDD table, the very first thing you should look at is what SSD were those measurements taken, because that affects the values. Two, In clinical setup, it is often necessary to convert PDD values from one SSD to another. And we essentially do this with the use of what we call the Menard factor. If you look at this formula, you can clearly see, before we even talk about this, let me not skip the points here. When you look at the formula that defines the PDD, there are three important factors that determines the shape of a depth dose curve. You have the inverse square law factor, which is this guy in bracket. You have the attenuation, the exponential attenuation within the tissue. And then you have the build-up factor, which is the build-up that happens before Dmax. Now, when we look at the formula, there are three key terms. One, SSD, which is controlled by the inverse square law. Two, the depth. Remember, the dose at different depths varies because of attenuation. And the field size directly impacts PDD because of varying amount of scatter radiation contributed to the dose at depth, because larger field sizes typically generate more scatter, which in turn contribute to an increase in the dose at greater depths, which in turn leads to higher PDD values. Now, regarding measurement considerations, there are key things here that I want to mention that I think are really crucial, which are also mentioned in TG71. One, we need to be aware of the field size influences when we are measuring our PDDs. And so remember that colorimeter settings do not directly determine PDD, since it is dependent upon the relative ratio of dose at different depths, and which in turn is influenced by scatter and attenuation. Now, two, TG51, which in turn provides, guidelines on the measurement of depth dose curves for photon and electron beams, essentially asserts that we need to use either cylindrical or spherical ionization chamber, which requires special attention with respect to the effective point of measurement. In other words, curves, and the red graph is shifted upwards by 0.6 R curve to take into consideration, keep in mind that the depth ionization curve, the blue graph, must be shifted to shallower depths or upstream by a distance equivalent to 0.6 times the cavity radius. For photon beams, when we are using cylindrical ionization chambers, this correction is essentially crucial to align the ionization data with the actual absorbed dose data. Now, one common question that we get, especially in board questions, is really to differentiate between PDDs or depth ionization curves. Now, for photon beams, this is important. For photon beams, the variation in electron spectra is minimal or small past the point of maximum dose, or past Dmax. What does this mean? It implies that the stopping power ratios between water and air becomes negligible, which implies that the depth ionization curves can be treated as equivalent to depth dose curve for photons. This is not true for electrons. For electrons, this equivalence does not hold true. Why? Because as electron beam loses energy, typically the electron beams lose energy more significantly with depth. The consequence is that the stopping power for electrons significantly varies with depth, which necessitate a correction to convert the depth ionization curve for electrons into an accurate depth dose curve. Now, without these corrections, keep in mind, without these corrections, errors between about 3 to 5% may be introduced in the PDDs at the reference depth. And lastly, we can convert, when we measure PDDs at different SSDs, conversion is essentially necessary to relate the PDD data between these different setups, which is why I said before, when you look at a PDD table, it is critical that you know what SSD it was measured. If you want to perform a calculation at an SSD that it was not measured, it is very easy to convert PDD measured at one SSD to PDD measured at another SSD through a bridge, using the Minerd factor and the TPR. Now, when you look at this equation down here, it looks a little complicated. The derivation is pretty straightforward. But the point I want to make here is the PDD at SSD2 with respect to the PDD at SSD1 is equal to this factor, which takes into account the inverse square law multiplied by this expression. The point I want to make here is this expression in blue in bracket, the magnitude of the term in bracket here, if you look at the red cursor, typically changes minimally about less than 0.5% with depth, and so can be neglected. And so effectively, PDD2 divided by PDD1 essentially equal to the Minerd factor. And I think this is an important equation to think about. Now, to round this off, remember, PDD is a function of SSD depth and field size. When the energy of the beam increases or the field size increases, PDD increases. This is because a higher energy beam penetrates deeper. A larger field size results in more scatter contribution to the overall dose at depth. The second, we need to think about the effect of SSD and depth. Now, the effect of SSD is a little bit trickier. As SSD increases, the PDD also increases. Why does this happen? This is because the dose rate changes less rapidly at larger distances. Keep that in mind, which means that as the depth in the patient or phantom increases, the PDD itself decreases due to increased attenuation of the beam as the beam penetrates deeper. Now, when you take the ratio, what happens is that it causes an overall increase in the PDD, if you think about it carefully. Now, SD of 100, remember here, the normalization depth is 10 cm, not Dmax, but most tables in papers and books that you see will be normalized at Dmax. So when you look at the PDD table, always try to look at the conditions upon which they were measured. The next factor here is the tissue phantom ratio, or TPR. Now, TPR essentially is a crucial concept and primarily used to calculate the dose delivered at various tissue depths while keeping certain machine parameters constant. Commonly, TPR is defined essentially as a ratio of the dose at the specific point in a phantom at depth D to the dose at the same point at a reference depth Dref, which is measured typically in a water phantom. And this factor essentially provides an easy way to measure the dose in terms of ratios that are independent of the SSD, which makes it particularly very attractive and useful for isocentric MU calculations. Now, the few points that I want to stress here in terms of measurement of TPR values is that TPR can be directly measured in water or solid water equivalent phantoms. Now, the detector is typically placed at a constant distance from the source. As you can clearly see here, the detector is placed at a constant distance from the source. And what is varied is that the depth of the phantom is varied while the position of the detector is constant, which means that the distance between the source and the point of interest stays the same while the depth is changed. A few things to note here that concerns PDDs and TPR. A few important points to note. One, as the field size increases, the amount of electron contamination from the treatment head of the machine also increases. What this means is that larger field sizes in turn result in a higher electron contamination, which effectively reduces the depth of maximum dose. On the other hand, increasing SSD reduces electron contamination because electron diverges more in air before they reach the phantom surface. Now, the depth at which the dose is maximum is influenced, one, by the fuel size, and two, by the SSD. An increase in fuel size correspondingly increases electron contamination, and Dmax tend to move closer to the surface. As the SSD increases, electron contamination decreases, which result in Dmax moving deeper into the tissue. That's just the point that I wanted to make. Now, it is recommended that the reference depth for all field sizes and SSD should be chosen based on the smallest field size required to achieve, lateral electronic equilibrium. This is essentially because for small fields, lateral scatter must be adequate to provide consistent dose deposition within the area of interest. Now, this formula here essentially tells us that we can calculate our TPR. Remember, TMR is just a special case of TPR from our PDD values. Remember, TPR is independent of SSD, which is independent of SSD, and to some extent, it's a measure of attenuation in tissues. The next point that I will briefly mention here, there is a lot that goes into wedges. And so there are essentially two kinds of wedges. You have physical wedges, which are rarely used, and you have non-physical wedges or electronic wedges, which essentially are often used. Now, a non-physical wedge, which is common for variant machines, is an electronic field that generates a tail dose distribution profile similar to what a physical wedge does. And this essentially happens by moving one of the collimating jars from one end of the field to what that goes. I've included the details, but for the sake of time, I'm going to skip all these exquisite details for your perusal later on, and we will move straight to this slide. Essentially explains how the wedge factor is calculated for enhanced dynamic wedges over EDWs for variants. And we typically do these with the use of what we call the segmented treatment tables. And the segmented treatment tables here relates the jaw position to the fraction of the total monitor unit setting. It's really interesting how this is calculated, but for the sake of time, I'm going to skip here. Now, off-axis ratio essentially is a fundamental concept in radiation therapy that describes how the dose varies at different positions away from the central axis. And this essentially is defined as the ratio of the dose at the point located off the center axis to the dose located at the point at the same depth on the central axis. There are key points that I want to mention for OARs that you need to take note of. The shape of the dose profile changes as the depth increases. Now the profile tends to widen with increased depth because of beam divergence. Two, there are horns. When you look at the 4MV, you could see that there are horns. The question is, horns represent regions of higher intensity produced, and typically they are as a result of the presence of flattening filters, and they are more pronounced at shallower depths and diminishes as the depth increases. The rationale for the creation of horns is due to the fact that is due to the gradual decrease in photon flowings away from the central axis, partly caused by in-scatter and out-scatter imbalances and changes in the effective beam quality as the depth changes. And the concept of radiological depth determination, which really is important. Now, before we do, let's now dive deep into, we have about 10, 15 minutes. Let's dive deep into some examples. Now, before we do examples, there are a couple of important facts to remember here. One, SC is a function of the collimator setting. SP is a function of the size of the field at the normalization depth for an SSD beam at depth of calculation for an SAD beam. Now, depth dose factors are a function of field size at the phantom surface for SSD beams and field size at depth for an SAD beam. Now, when calculating the monitor, you have to calculate the monitor unit per field for a given description, which implies that for multiple fields, the dose per field is calculated using beam weights. And this formula here kind of gives you the dose for a particular field I is calculated as a proportion of the beam weight with respect to the prescribed dose. Now, if the primary physician then prescribes the dose to a specific isodose line, then the dose per field is simply the given by DI divided by the isodose line, or the LDL, where in this case the IDL, sorry, is the isodose line that is prescribed to that particular dose. So the first example here is we have a 6MV beam at 100 cm SAD with 0.8 centigrade per MU dose rate at the normalization point. And keep in mind that the normalization point here is 10 cm. The equivalent square, and we're required to calculate the MUs required to deliver 250 centigrade to the isocenter. Now, keep in mind that the collimator size, as defined by the field, is by the question is 10 by 15 cm squared, and the depth of calculation is 6, and there is no blocking. These are the crucial things that we need to pay attention. The very first step that we need to calculate here is the equivalent square field at depth, and we're using the Stirling formula. It gives us 12 cm. Now, the dose is then calculated at the isocenter point. The beauty here is that the isocenter point is 100 cm, which means that the inverse square law is 1, and the field size is defined at depth of the calculation point. And the TPR, so we now get the TPR from the table. Remember, the field size is 6 by 12. And so if we do that, sorry, it skipped here. If we do the calculations, it kind of simplifies here beautifully. And our answer gives us 266 MUs. 266 MUs. And so the critical point that I want to mention here is when you're doing your calculations, be careful. Be careful. We have how you define your SP. Remember, SC is defined by the collimator setting, and SP is defined by the field size at depth. And essentially, we use the equivalent square method as well as similar triangles to be able to calculate our equivalent square field at depth. We have about 6 more minutes. Now, this example here is an example of a block field, in which case we have a 6 MV beam. Always look at the normalization conditions. 100 cm SED with a normalized to 0.8 centigrade per MU at the normalization depth is still 10. We're asked to determine the number of MUs required to deliver 90 centigrade to the isocenter of an AP long field as shown in this diagram. The collimator setting, is 18 by 12, and the physical depth in this particular case is 10 cm. The field is blocked using a tertiary MLCs, and the 15-degree physical wedge is added to the field. Remember, it's clearly stated here, we're going to use the TPR method. This is the formula. I have completely taken away the inverse square law because the question at hand, we are calculating this at the isocenter, which simplifies the equation. Now, the point I want to note here is this is our calibration. SC is different from SP because SC is defined by the collimator settings, and SP is defined as the field size at depth. And so we have to use the equivalent square to calculate this, from which we then determine our TPR and W and the wedge factor with the use of tables provided to us. And we simply substitute and have our answers. At this point, I will just stop for discussions and questions if you have those. But we are essentially on slide 56, and there are actually 93 slides. I have ample examples that we will send the slides to you to look through to be able to see the various aspects of MU calculations. Thank you, everybody. If you have questions, we can discuss those. If you have questions or comment or contribution, I would love to hear those, please.
Thank you very much, Honor. Hold on, let me cut off the recording.